Welcome to my Physics Lab 4 report. We'll have an introduction, some fundamental principles and models, experimental observation, results, analysis, and some discussion. So in this lab, we used a simulation to better understand RC circuits and their interactions. The goals were to use an ammeter and a voltmeter to measure current and voltage, and then also use some of that data to find the time constant RC of a circuit. That was found to be 5.95 seconds, and then in addition, as resistance of a light bulb increased, time to charge and discharge a capacitor increased as well, and then calculating the experimental values was very close and equal to the simulated values. So some fundamental principles and models, we have the node rule, basically at a node or an intersection, the total current in equals the total current out, and then the loop rule, which states that the total potential drop for a closed loop circuit has to be equal to 0. The potential drop across a resistor is Ohm's law. That's the drop is going to be equal to the current times the resistance. And then in parallel and series, as we can see on the bottom, the inverse resistances add up in parallel, and they just add up directly in series. For a capacitor, this equation can be rearranged, and we can see that the potential drop is going to be equal to Q divided by C. And then the series and parallel is the exact same as for resistors, except it's just flip-flopped. So, i.e., inverses would sum in series instead of parallel. Since this is using simulation software, the only real assumption is that the software is accurate. And then in addition, towards the end of the lab, some data was taken. We had to estimate a line of best fit, and then that could lead to some error, but we'll talk about that towards the end. The system was the measurement tools, and the surrounding was the circuit. So let's get into it. So for part 1, pretty simple circuit here. 2 batteries, 1.5 volt EMF each, which means 3 volt EMF total. You can add up the resistors because it's in series, 147 ohms, and then using that equation you can get 0.0204 amps, and that's confirmed by the current shown in the picture. In a normal ammeter, if it were to be flipped around, that reading would be negative, but as we can see here, in the simulation, the direction doesn't matter, it's always positive for some reason. Then in part 2, we replace the bottom ammeter with a voltmeter. The voltmeter doesn't allow any current to go through it, so that's going to cancel out all current, as we can see, current 0. However, it does still measure the voltage to be 3 volts. In part 3, we replaced that voltmeter with just a wire, and then we measured all of our potential differences. So from A to B here, we have 3 volts, that's the batteries. B to C is just a wire, so it's 0. C to D is the first resistor, negative 0.96 volts. D to E is 0, it's just a wire. E to F is negative 2.04 volts, that's the second resistor, and then the rest is 0. So if you see here, the total is 0, which is the loop rule. The voltmeter doesn't change the ammeter readings because current's not going to flow through the voltmeter, it's just touching the circuit, and the current keeps going through the circuit. And the graph to the right shows the value of the total voltage change as a function of time. So this is right after the battery, it's at 3, first resistor goes down, second resistor goes down to 0, and then stays at 0. So then in part 4, we set up this parallel little circuit, side circuit here, and you can see that all the current goes through the ammeter because it has 0 resistance. This then means that this resistor basically isn't part of your equation, and if you go back to part 1 and redo the equation with just 47 ohms, you'll see that the current is 0.06 amps. And then here are some calculations. These came from the rounded values that the simulation software gave, so they're a little bit off, but you can see that everything calculates out to be the exact same. Then in part 5, we were using a light bulb here as a resistor to charge and discharge a capacitor, and the times are given down here for how long it takes to charge and discharge with different resistances of a light bulb. And finally, in part 6, we basically did that same setup, charged up the capacitor, and then removed the battery to allow it to discharge and took data over 20 seconds. So for about every 1 second, data was taken, and then we used this equation down here to plot the points in Desmos as seen in the picture. A line of best fit was then estimated, and the slope of that line was about negative 0.168. The time constant can be solved for through an equation using that slope, and it comes out to be 5.95 seconds. Now R is 30 ohms and C is 0.2 farads, so R times C is 6 seconds. So we can see that our experimental data and the actual calculation are very, very close. Some possible sources for error there is that it was an estimated line of best fit. It could be some rounding errors due to the low precision of the simulation, rounding errors due to calculator and or Desmos, and then also there's always a possibility of human error. So getting into the additional questions. Essentially, this one is saying, what if you use an actual ammeter instead of a simulated ammeter? What is the difference? Well, a real ammeter does have some resistance, even if it's very small. The virtual has exactly 0. This statement's going to also be true for the wires in a real-life situation. This would decrease the current in the circuit a little bit, leading to lower readings on the ammeters as they would be acting as additional resistors. And then this one is essentially saying, if you were to use just a battery and a capacitor, what would happen? Well, the simulation predicts the capacitor would charge instantaneously. This would not happen, though, in real life, as the wires do have resistance, the capacitor has some resistance. The current would be extremely high, but it would not be instantaneous charging. Thank you for watching, and have a great rest of your day.